Hi, welcome back. So we're in chapter 3. You must know add the outline of a mathematical constant number and its natural logarithm, the ln. So we got a constant now, and the indeterminate is the power, right? We have this case here. What is the behavior of the slope when we have this case here? In a geometrical way, it means by multiplication increasing. What is the behavior of the y? It's 100% on the previous value, 50% on the next value. Depends on whatever is my base. Here it was the value of y was constantly growing. So imagine I have a previous value of y and the next value of y. Now the difference between them, this ratio, this value, it's 100% of the previous and 50% of the next. If I would have base of 2. How about if the base was 3? 200% of the first value and 66.66% of the next value. We have seen that it seems to be the difference between them, whatever the base is, in this case my constant, minus 1 multiplied by 100. In other words, here if my base is 3, that will be 3 minus 1 multiplied by 100. That is 200%. Now let's take a base that is equal to e, 171.82, and the next 63%. All right, so we have just studied the behavior when we have a constant on the base indeterminate of the x. Now what I'm going to do, let's imagine that I have a timeline here. All right, start at this point and end at this point. Let's assume that somehow we have a certain element. Every stop at the end of this stop on the red line here, right? This element double itself. It becomes twice as much. That means at this particular point, this point will be 2 points. All right. Let's make number of these lines here. So what we could see here, the 2, then each one of them will double itself. So this is the first point and this is the second point. And in the third stop, each one of them will double again. So these are quite a bit familiar numbers for us, right? Why? Because we know now what is the base of this growth. It is base of 2. Once again, I can actually illustrate this in the form of logarithm. I hope now you are putting all the information together, how the log, it just in tandem with the idea of the power. So you could change this one to become 3, for example. It means 1 point, it makes itself by 3 times. Now what I am interested in actually to show you or to study the growth of this behavior when the log was base 2. Let's look at the actual growth from this point to this point. So we could see the difference between them is 100% of the previous one, and it's 50% of the second one. Now let's take this concept and try to evolve it a little bit in a different way. Let's say, for example, I would have here a value again of 1. When it get to the end of this line, it grows by 171.8%. So what do you think the value then will be here? That will be 2.718. Now what does that mean? That the base here, it's actually 2.718. Previously, the base here was 2. That means at each point here, we will grow by the exact same value. Again, imagine I would have a base of 2. Happens to be 100% growth from the previous one. Let us take this 100% into 50% and 50%. It means that 1 here, I have a value here, which is 50% of the previous one. That means 0.5. Now the total is 1.5. And then I would have a 50% on the 1.5. That will lead me to 0.75. So in total, that will be 2.25 or something like that. All right. So what is the comparison now? You could see quite clear. The 100% was constant. I was getting exactly equivalent to the base of 2. But when I divided the rate of increase, this 100%, the base increased by that much. As if I am working on a new line, that will be 2.25. Now the base here was 2, now the base here is 2.25. Let's try again to manipulate this 100 further and cut it into 4 different pieces. I have actually created here short code just to illustrate what I was saying. Let's divide this into 2. So the value become 225, as if my base now is 2.25. Let's divide this into 4. So what the base become now, the base become 2.444. Let's divide this into, say, 12, which is 8.3 for each one. So this become my base. Let's increase this number by quite a large number, say 10,000, for example. You will get 0.01% for each period of time. Now, essentially, you will get the value of 1 and 0.01% interest, then 0.021, and so on and so forth, until the end, the value of 2.71814, etc. This is again is going to be my base. Now, is this number familiar to you? This is the value of the E. So basically the value of the E, that you take the base, which is started actually with base 2, and I know the growth of base 2 is 100%. Divided this 100% into small pieces. However, somehow it started actually to stuck at a certain value and it didn't grow no more. And that was the value of the E. This is actually, I think, the exact path how the scientist Euler reached out to the discovery of this particular number, which is quite a bit interesting. Now you might wonder, how about if I change actually the power from 2 to become 3? So when I come back to my example here, I will say the rate is not 100% of that growth. Let's make it 200%. Let's run this and see what we got. It just went to 7.38. You might say we have just discovered a new irrational number. Now you take the value of E, raise it to the power of 2 because 200%. You get the value of 7387. So if I go change the base to 4, 300% extra growth from the first value, as if taking E to the power of 3, you will get the value of 20. So the base will be 20.08. And the main property of this number, when we have seen basically before as a base, it turns out that the slope is just equal to the function itself. Last, actually, we have just to explain the meaning of the ln, the natural logarithm, which is in relation to this. As we said, the constant to power of x, for example, we got like 2 power of x, 3 power of x, or whatever. We have seen that the reverse of this, it should be its logarithm, right? Which is log to that base of a certain value that will actually equal to the x. This is exactly the same when we talk about this base to be actually e to the power of x. What is the log of base e of any value? It will be equal to that x. Now, usually this term has been written as ln, which we call the natural logarithm of e. So ln of v is equal x. It's exactly equivalent to the meaning of log e to the v is equal x. Now, from a graphical perspective, maybe we can see that by saying so y is equal e to the power of x. This is my essential function, and I would like to get the inverse of this. The inverse will be y is equal log to the base of e of that x, which is exactly equal to this. Now, if I want to write it, y is equal ln of x, you could see it is the same. So basically, we have reached out to the end of this session, and now we are ready actually to discuss something you must be completely familiar with, derivative and integrals. And that's exactly what we're going to do next. I'll see you then.